Hello friends, welcome back to my channel Maths by Samit Deshmukh. In this video we are discussing definition of inverse function. Then we will prove one standard formula to find out derivative of inverse function. This formula is nothing but one of the theorem, and applying this formula we will prove some standard formulas to find out derivative of inverse trigonometric function. So if you are new on my channel, subscribe the channel and hit the bell icon so that you will get notification of every newly uploaded videos. So in definition of inverse function we have studied in class 11th in detail. Just we are revising this definition in short. Even we have studied about inverse function in detail in trigonometric function. Trigonometric function is one of the chapter in first paper of mathematics, third chapter from first section, means first part. In that case also we have seen what is the definition of inverse function. So let us revise the definition of inverse function. If f is a function from set A on set B, let us denote here first set by set A and second set by set B. And here what we are saying here, f is a function from set A on set B which is 1 1 and on 2, then its inverse function is denoted by f raised to power minus 1, and it is a function from set B on set A. Means f is a function from set A on set B which is 1 1 and on 2. At that time only inverse function exists. Inverse function means the function from set B on set A is denoted by f raised to power minus 1, and it is called as inverse function of f. Means if f is function from set A on set B, then the function from set B on set A, if it exists, it's called as inverse function of f. Now here I am supposing that the element of this set is say x, and image of this x under the function f I am denoting it by y. So symbolically it will be denoted by what? F of x is equals to y. Means image of x under the function f will be equals to y. Symbolically it will be denoted by this notation, and here it is given to us that this is the second definition. Means either the definition is written in this form or the definition is written in this form also. So y is equal to f of x is a function. So here a function we have denoted by f of x, or it here can also be denoted by what? Y, which is 1 1 and on 2. If this function is 1 1 and on 2, at that time only inverse function exists, and inverse function exists, then it is denoted by this notation f raised to power minus 1. Means image of y under this function, image of what? Y under which function? F raised to power minus 1 will be equal to what? X, which can be written as x is equal to f raised to power minus y. Means here x is equal to f raised to power minus y. And when this inverse function exists, if this function is 1 1 and on 2, at that time only inverse function exists. Simply we have to remember that if f is a function from set A on set B, then the function from set B on set A, if it exists, then it is called as inverse function of f. Applying this definition now, let us try to solve this example. Let us try to prove this theorem. This is nothing but theorem to find out derivative of inverse function. So y is equal to f of x. Here y is equal to f of x is a function, means image of x under the function f will be equal to y. So this is the meaning of this symbolical representation. Is a differentiable function of x. Differentiable function of x means what? Y is differentiable function of x, then symbolically it will be denoted by this notation dy upon dx. It is given to us that y is differentiable function of x. Means derivative of y with respect to x exists. And then according to definition of differentiation, if this derivative exists, means limit delta x tends to 0, delta y upon delta x, this limit exists. Means if this limit exists, at that time we can say that function is differentiable, but it is already given to us that function is differentiable, means this limit is already exists. This is the given condition, and it is given to us that this function y is 1 1 and on 2. If function is 1 1 and on 2, means its inverse exists, and it is also given to us that the value of derivative is not equal to 0. Also x is equals to f raised to power minus y, means it is the notation for inverse function, means inverse function exists, and when it is exist, if the function is 1 1 and what? On 2, at that time inverse function exists. Then we have to prove that this x is differentiable and dx upon dy is equal to 1 upon dy by dx, or it can be written in this form also. The derivative of this inverse function will be equal to 1 upon f dash of x. Both the meaning of both the notation is one and the same. So let us try to prove this theorem. So here we can easily observe that image of x under function f is y. If the value of x changes, let us denote the change in the value of x by delta x. Means delta x is the increment in the value of x. As the value of x changes, its image is also changes, means there will be corresponding change in the value of y. Let us denote the change in the value of y by what? Delta y. So what we are supposing here in the proof, let x changes to x plus delta x. Let x changes to x plus delta x. Correspondingly, y changes to y plus delta y, isn't it? So definitely as value of x changes, means value of y also changes. Change in the value of y we have denoted by delta y, means increment in the value of y we have denoted by delta y. Now to prove this theorem we will require one result. First let us try to prove that result and denote it by equation number first. Later on we will use that result to prove this formula to find out derivative of inverse function. So what is that result? Try to understand. As delta x tends to 0, we are trying to find out value of delta y. That delta y tends toward which number? That we are trying to find out here. So keep this delta y as it is. Just simply I am dividing by delta x, and that's why I am multiplying by delta x. Again, if delta x will get cancelled, we will get what? Delta y. Just simply divided by delta x, that's why multiply by delta x. Now here if you will observe that the value of delta y upon delta x as delta x tends to 0 will be equals to value of delta y upon delta x as delta x tends to 0 will be equal to dy by dx. This is given condition, means value of this first term will be equals to dy by dx. It is given to us that y is differentiable function of x, means this derivative exists, means this limit exists, means value of delta y upon delta x as delta x tends to 0 will be equal to dy by dx. Now this delta x tends to what? 0, and 0 into any number will be equals to 0. So what result we have got here? As delta x tends to 0, so this implies that as delta x tends to 0, this delta y also tends to 0. Delta y also tends to 0. Let us denote it by equation number first. Now if you will observe our required result, so on this side dx by dy is there, so that's why we are considering here delta x by delta y. This is the step which we are taking randomly, observing our required result. Okay, जैसे हमारा जो result हमें proof करना है, हमारी left hand side dx by dy है, तो हम यहाँ पे delta x by delta y लेंगे. अब ये right hand side मिलने की कोशिश करेंगे. Let us try to get our result on the right hand side. So which is equal to, now simply I am dividing to numerator and denominator by delta x. Let us see what we'll get if I am dividing to numerator by delta x. If I am dividing to this numerator by delta x, so here we will get 1. So we are dividing to numerator by delta x, that's why we have to divide to denominator also by delta x. What we'll get if we are dividing to denominator by delta x? Here we will get delta y upon delta x, means this term can also be written in this form. Again if we are simplifying it, we will get the same result. ये term divided है, multiply किया तो इसका reciprocal लेना पड़ेगा, तो हमें वापस से ये result मिलेगा. So just we are doing this adjustment to get our required result. Now we will taking limit on both sides. So take limit as what? Delta x tends to 0 on both sides. So taking limit as delta x tends to 0 on both sides. Let us see what we'll get. So therefore on this side we will get limit delta x tends to 0 delta x upon delta y. Just simply we have taken limit as delta x tends to 0. On this side also take limit delta x tends to 0 1 upon delta y upon delta x, keep it as it is. Just simply we have taken limit as delta x tends to 0 on both sides. So now observe this left hand side very carefully. So here delta x tends to 0 can be replaced by delta y tends to 0, because we have already proved that as delta x tends to 0, delta y also tends to 0. So since in the denominator delta y is there, so here also will require delta y tends to 0. So that's why delta x tends to 0 can also be replaced by delta y tends to 0 from equation number first. So let us see what we'll get on the left hand side. So on the left hand side, what we'll get, limit delta y tends to 0, delta x upon delta y, keep it as it is. On the right hand side, we are taking limit of both numerator and denominator separately. Let us see what we will get if we are taking limit of numerator. So in the numerator, we will get limit delta x tends to 0. What is the numerator? 1. And in the denominator, what we will get, limit delta x tends to 0, delta y upon delta x. Just we have taken separate limit of this numerator and denominator. Okay, so here this delta x tends to 0 can be replaced by delta y tends to 0 from which equation? First. So give a reason from equation number first. We have replaced delta x tends to 0 by what? Delta y tends to 0. Now on the left hand side, keep this term as it is, limit delta y tends to 0, delta x upon delta y, keep it as it is. What is the limit of constant term? Limit of constant term is a constant, because there is no variable. If delta x appears, we are able to replace delta x by what? 0. But the term of the variable does not appear, means numerator is a constant function, and we know that limit of constant function is constant. We are not disturbing to denominator. In the denominator, limit delta x tends to 0, delta y upon delta x, keep it as it is. Let us denote this equation, say by equation number 2. Now we are using given condition. What is the given condition? Y is differentiable function of x. It is given to us. Since y is differentiable function of x, so we can say that dy upon dx exists. Y is differentiable function of x, symbolically can be denoted by what? Dy upon dx. And if this derivative exists, means which limit exists according to definition of derivative? Limit delta x tends to 0. अगर dx है यहाँ पे, तो यहाँ पे delta x tends to 0 लेना है, और यहाँ पे dy है तो यहाँ पे delta y, और यहाँ पे dx है तो यहाँ पे delta x. This result simply we are getting applying what? Definition of differentiation. So now here what we have got according to given condition, that this limit delta x tends to 0, delta y upon delta x exists. Why we can say that this limit exists? Because it is given to us that y is differentiable function of x, means derivative of y with respect to x exists. And when we can say that differentiation exists, means if this limit exists, isn't it? It is already given to us that function is differentiable, means this limit is already exists. Now observe this right hand side of equation number 2. So this limit exists, means dy upon dx exists, and it is given to us that dy upon dx is not equals to 0, means denominator is not equal to 0, means any number divided by 0 is what? Undefined value. But denominator is not equal to 0, means this value is defined value, means we can say that therefore limit on right hand side of equation 2 exists. This limit exists and its value is not equals to 0, and limit delta x tends to 0, delta y upon delta x is not equal to 0. It is given to us that this dy by dx is not 0, means this limit also not 0. And if this denominator is non-zero number, means we can say that on this value we will get defined value. If denominator becomes 0, at that time we can say that value is undefined. But according to given condition, this denominator is non-zero number. So if this limit exists, means what? Its value is one number. तो यहाँ पे एक number मिलेगा, दोनों number का division एक number ही होगा, and that number is nothing but value of what? This limit. अगर ये limit exists होता है तो इस पे ये depend है left hand side, means we can say that limit on left hand side also exists. So therefore limit on left hand side of equation second also exist. And if this limit exists, then according to definition of differentiation, it will be denoted by what? Dx by dy, and is denoted by dx by dy, and is denoted by what? Dx by dy. So if we are substituting all these value in equation number 2, let us see what result we will get. So therefore equation 2 becomes, so this left hand side will be denoted by dx upon dy. Dx upon dy is equals to, on the right hand side keep this numerator 1 as it is, and this denominator will be denoted by what? Dy upon dx. Dy upon dx. And in this way we have proved a very important formula to find out derivative of what? Inverse function. Means dx upon dy can be written as 1 upon dy upon dx. So if you'll observe this result very carefully, so while solving the example or while whenever we are proving the standard formulas to find out differentiation, means derivative of inverse trigonometric function, this result can also be written as, means this dy by dx will get multiplied on this side. So on this side we will get dy upon dx, and on this side this dx upon dy will get divided on this side, means 1 upon dx upon dy. So sometimes we are using this result also while solving the example, or whenever we are proving the standard formulas to find out differentiation of inverse trigonometric function. Meaning of both the term is same, just we are using transformation. ये term इधर divided है, इधर multiply होंगे, और ये term multiply इधर आके क्या होंगे? Divided. So means sometimes this formula can also be used while whenever we are proving the standard formulas to find out differentiation of what? Inverse function. Especially we are studying about what? Inverse trigonometric function. So applying this standard formula to find out derivative of inverse trigonometric inverse function, we will prove the differentiation of inverse trigonometric function. Total 6 formulas are there to find out differentiation of inverse trigonometric function. Which are these formulas? Derivative of sin inverse of x, cos inverse of x, tan inverse of x, sec inverse of x, cosec inverse of x, and cot inverse of x. So let us apply this formula to find out differentiation of inverse trigonometric function. Now let us try to prove some important formulas to find out derivatives of what? Inverse trigonometric function. So which is the first inverse trigonometric function? That is sin inverse, and we have to prove that the derivative of sin inverse of x is equals to 1 upon under root 1 minus x square. So let us try to prove this result. Already we have seen a theorem to find out derivative of what? Inverse trigonometric function. Applying that formula, we have to prove this formula to find out derivative of what? Sin inverse of x. So here we have considered this function y is equal to sin inverse of x. If we are taking sin on both sides, so on this side we will get sin y, and on this side if we are taking sin, so sin and sin of sin inverse of x will be equal to x according to properties of inverse trigonometric function. In the next video I will provide you all the properties of inverse trigonometric function, and these properties even we have proved in trigonometric function, means third chapter from our first paper, which is that chapter trigonometric function, and last article of this chapter is inverse trigonometric function. At that time we have proved all the properties of inverse trigonometric function, but we will prepare a list of all these properties, and in the next video I will explain once again these properties also. Just simply we have taken sin on both sides. On this side we will get sin y, and on this side sin, if we are taking sin, what we will get? Sin of sin inverse of x will be equals to x. So this can be written as, that is x is equal to what? Sin y. X is equal to sin y. Now I am differentiating both sides with respect to y. Let us see what we'll get here. So differentiate with respect to y. On this side we will get dx upon dy, and on this side derivative of sin y will be equal to what? Cos y. So dx upon dy, keep it as it is. Now this cos y, can I write it as under root cos square y? Yes, cos y can be written as what? Under root cos square y, which is equal to, again according to identity, cos square y can be replaced by 1 minus sin square y, because we know that cos square theta can be written as 1 minus sin square theta. So which is equal to under root, keep it as it is, 1 also as it is, minus also as it is. Now sin y, what is sin y? Sin y is equal to x, means sin square y will be equals to x square, which is nothing but value of what? Dx upon dy. Let us denote it say by equation number first. Now we have proved one theorem. So what is our theorem? That dy upon dx is equals to 1 upon dx upon dy. So keep this dy upon dx as it is, in the numerator 1 also as it is. Now just simply I am substituting the value of dx upon dy. What is the value of dx upon dy? Under root 1 minus x square. So dx upon dy is nothing but denominator here, and I am substituting its value is equal to under root 1 minus x square. This value we are substituting from equation number first. In this way we have got our required result, that dy upon dx is equal to 1 upon under root 1 minus x square. Already in case of inverse trigonometric function, we have seen that domain of sine inverse of x is in between -1 and +1, and its range is in between what? -π/2 to +π/2. This part we have already discussed in very detail in first in trigonometric function, means in first paper, third chapter, trigonometric function, and last article is what? Inverse trigonometric function. At that time we have already seen what is the domain and what is the range of every inverse trigonometric function. So in this way we have got our required result. Now let us try to prove the second formula to find out derivative of cos inverse of x, and here we have to prove that its derivative is -1 upon under root 1 minus x square. So here we are considering the given function y is equal to cos inverse of x. Here also simply taking cos on both sides. So on this side we'll get cos y, and on this side cos of cos inverse of x will be equal to x. So which is equal to cos. On this side what we are getting? Cos y. So x is equal to cos y. This can be written as cos y is equal to x, can be written as x is equal to cos y. Now simply we are differentiating both sides with respect to x. So derivative of with respect to y, derivative of x with respect to y is dx upon dy, and derivative of cos y with respect to y is minus sin y. So minus, keep it as it is. Sin y, can I write it as under root sin square y? Yes, sin y, what is square root of sin square y? Is sin y. So sin y can be written as under root sin square y. So which is equal to under root, keep this minus as it is, and sin square y according to identity can be replaced by 1 minus cos square y. Now we are replacing this cos y by its value x. So minus, keep it as it is, under root 1 also as it is, cos y means x, so cos square y means x square. In this way we have got the value of dx upon dy, and now substitute this value in our formula which we have proved as an theorem. So what is that theorem? Dy upon dx is equal to 1 upon dx upon dy. So keep numerator 1 as it is, dx upon dy from equation number first, its value is equal to minus under root 1 minus x square. Here I am writing minus, and dx upon dy is minus under root 1 minus x square. So just we have substituted this value in this expression, and we have got our required derivative. Now let us try to find out derivative of tan inverse of x. So first consider the given function y is equal to tan inverse of x. Again, if you are taking tan on both sides, on this side we will get tan y, and on this side tan of tan inverse of x will be equal to x. Means what value of x we have got here? Tan y. Now I am differentiating both sides with respect to y. So on this side derivative of x with respect to y is dx upon dy, and on this side derivative of tan y will be equal to sec square y. Now this sec square y according to identity can be written as what? 1 plus tan square y. Just simply we are applying fundamental identity. Sec square y can be written as 1 plus tan square y. 1, keep it as it is. We know that tan y means what? X. So tan square y means what? X square. Let us denote this result by equation number first. Here we have got the value of dx upon dy. Now remaining part is just to substitute the value of dx upon dy in this formula, which is nothing but a formula to find out derivative of what? Inverse trigonometric function. So dx upon dy we are replacing by its value 1 plus x square. So here in the numerator 1, keep it as it is, and in the denominator dx upon dy can be replaced by 1 plus x square, and in this way we have got the derivative of tan inverse of x. What is derivative of tan inverse of x? 1 upon 1 plus x square. Now let us try to find out derivative of cot inverse of x, and we have to show that its derivative is minus 1 upon 1 plus x square. So first we are considering the given function y is equal to cot inverse of x. Now we are taking cot on both sides, so on this side we will get cot y, and on this side cot of cot inverse of x will be equal to x. So x will be equals to cot y. Now we are differentiating both side with respect to y. On this side already derivative of x is with respect to y is written here. So derivative of cot y with respect to y is minus cosec square y. So minus, keep it as it is. Just simply this cosec square y can be replaced by 1 plus cot square y according to fundamental identities in trigonometry. Cosec square y can be replaced by 1 plus cot square y. So minus, keep it as it is, 1 also as it is, cot square y. Cot y means x, so cot square means x square. In this way we have got the value of dx upon dy. Remaining part is just to substitute this value in this formula. So in the numerator 1, keep it as it is. In the denominator we are substituting the value of dx upon dy, which is nothing but minus in bracket 1 plus x square. So here in the numerator I am writing minus, and in the denominator I am writing 1 plus x square. So minus 1 upon x square is the value of what? Dx upon dy, and this is nothing but derivative of cot inverse of x. Now let us try to find out derivative of sec inverse of x, and we have to show that its derivative is 1 upon x under root x square minus 1. So consider the given function y is equal to what? Sec inverse of x. In every case we are using same method. So here take sec on both side. So on this side we will get sec y, and on this side if we are taking sec of sec inverse of x will be equal to x according to property. So on this side we will get x, so means x is equal to what? Sec y. Now we are differentiating both side with respect to y. So derivative of x with respect to y is dx upon dy, and derivative of sec y with respect to y is sec y into tan y, isn't it? Now keep this sec y as it is. Can I write this tan y as under root tan square y? Yes, tan y can be written as what? Under root tan square y. Again, if you are simplifying, square and root will get cancelled and we will get what? Tan y. Just we are trying to convert it in terms of sec. Why we are trying to convert it in terms of sec? Because sec can be replaced by x and our required answer is in terms of x. That's why I am writing tan in terms of tan square, so that we are able to apply fundamental identity, and using identity we are able to convert it in terms of sec. So here sec y, keep it as it is, so which is equal to sec y as it is, and according to identity tan square y can be written as what? Sec square y minus 1. Just simply we are applying our fundamental identity. Now we are replacing sec y by what? X. So here sec y will get replaced by x. Again under root sec square will get replaced by what? X square, because sec square y will be equal to x, means sec square y will be equal to what? X square. Keep that minus 1 as it is. Just simply we have replaced sec y by what? X. In this way we have got the value of dx upon dy. Only the remaining part is just to substitute this value of dx upon dy in this formula. So what result we will get? 1 upon dx upon dy. What is the value of dx upon dy? X into under root x square minus 1. In this way we have got the required derivative of sec inverse of x. Now let us try to prove the last formula, that is to find out derivative of what? Cosec inverse of x, and we have to prove that its derivative is minus 1 upon x under root x square minus 1. So consider the given function y is equal to cosec inverse of x. Here also we are taking cosec on both sides. If we are taking cosec on left hand side we will get cosec y, and on this side if we will take cosec we will get what? Cosec of cosec inverse of x will be equal to x. Means what value of x we have got here? Cosec y. Value of x will be equal to what? Cosec y. And as usual in every case we have seen that we are differentiating both sides with respect to y. What is derivative of cosec y? Minus cosec y into cot y, isn't it? So we are not disturbing to cosec, just simply I am trying to convert cot in terms of what? Cosec, and it is possible using identity. So minus cosec y, keep it as it is, and this cot, can I write it as under root cot square y? Yes. So because under root cot square y, after simplifying it we will get what? Cot y. So minus cosec y, keep it as it is, minus cosec y, keep it as it is, and according to identity cot square y can be replaced by cosec square y minus 1. Now we are just replacing cosec y by its value. What is the value of cosec y? Cosec y is equal to x. So here minus, keep it as it is, cosec y will be equal to x into under root cosec square y. Again can be replaced by x square because cosec y is x, means cosec square y is equal to what? X square. Minus 1, keep it as it is. In this way we have got the value of dx upon dy. Remaining part is just to substitute this value in this theorem, that dy upon dx is equal to 1 upon dx upon dy, isn't it? So we are replacing dx upon dy by its value. What is its value? Minus x upon under root x square minus 1. This minus I am writing it in the numerator, isn't it? And in the denominator write down what? X into under root x square minus 1. We are able to write minus here also, but the standard method says that always minus should be written in what? Numerator. Whenever we are writing fraction, if the fraction is given in this form, so at that time to write down it in the standard form, we are shifting minus in what? Numerator. This is the standard method of writing the rational number, or we can say that writing the fractions. So in this way we have proved all the 6 formulas to find out derivatives of inverse trigonometric function. In the next video we will discuss about properties of inverse trigonometric function, and applying these properties and these standard formulas we will see how to find out derivatives of inverse trigonometric function. So if you think that these videos are helpful to you, so like the videos and share these videos with your friends also.